Okay, we're going to go ahead and continue on with our notes. We left off yesterday with Euler's number or Euler's number, however you want to pronounce it. And when we talk about this number, it occurs, they say naturally in a lot of different places, right? So we'll talk about the application in a second, but let's talk about what the number actually is. It's also sometimes called Napier's constant. So I put that information down here too. And so what E is an irrational base, meaning that it's kind of like pi. It goes on forever and there's really no pattern there. And the reason why is because this is where we get it from. Okay, real brief reminder of your factorials. If I have, for example, 3 factorial, that's going to equal 3 times 2 times 1. Okay. And so the only other rule to remember is that 0 factorial is actually equal to 1. So when I look at this summation, right, this is the sum of, it's the Greek letter sigma, the capital letter sigma, from n equals 0 to n equals infinity. And from 0 to infinity, that's the equivalent of 1 over 1 plus 1 over 1 factorial, which is just 1, plus 1 over 2 factorial, which is 1/2, plus 1 over 3 factorial, which is 1/6, plus 1 over 4 factorial, which is 4 times 3 times 2. So that's 24, 1 over 24, right? And so that continues on forever. And we end up getting a value that is somewhat in the ballpark of, let me grab it here. It's about 2.71828. Often it's just approximated with 2.718. All right. What's interesting about this is that the inverse of E is the natural log. So if we want to get rid of an E, what we do is we multiply by the natural log to get rid of it. Graphing natural log and your E values are going to be inverse functions of each other. All right. Let's take a look at applications. We talked about exponential growth being part of compound interest. But E in particular is part of that. So compound interest. And of course that was Bernoulli. There is a gambling equation that deals with the probability of slot machines, the probability that they're going to hit a winner. Interesting enough, when the IPO or initial public offering for Google went out, their initial public offering was a whole number of the letter E, and also in their hiring, Google had a billboard that had a puzzle related to E, and if you solved that, you would get there's a place to submit it, and then if you solve that, it took you to a website, and that website had additional puzzles or problems to solve, and if you solved those, you were actually invited to submit your resume. So I don't know what the obsession Google has with Euler's number, but it is what it is, okay? So anyway, those are some of the applications that I find are kind of interesting. All right, let's graph exponential functions so we can talk about what happens when we look at transformations. All right, let's look at the function f of x equals negative e to the x minus 3. Now, something like this, we're going to dive into Desmos because I wouldn't necessarily expect you to be able to pull this up off the top of your head. So let's pull up Desmos. Okay, so here is, let me pull that. Here is what negative e to the x minus 3 looks like. Okay, remember when we did our transformations, minus means that we're moving to the right, plus means that we're moving to the left. So let's take a look and see what the originals look like and what happens. So I'm going to take this graph off, and I'm going to just look at graphing E. So this is what E looks like normally. And if I do negative E, right, it's going to reflect it across my x-axis. Now, if I use negative e to the x minus 3, right, very similar to my negative e to the x, but what has shifted, right? You've got a translation to the right. And we can talk about how much that, about what that translation is. All right. For now, what I want you to do is go ahead and pause this video and draw these on your paper. So make sure your notes have this in it. And then as soon as you are done, go ahead and hit play and we'll get back to our regularly scheduled programming. All right, so now that we know a little bit about what E looks like, maybe when we graph it, what some of the transformations look like, let's go ahead and, again, I apologize. I don't know why I'm having all of these typos. All right, solving exponential functions. Here's our kicker right here. If a to the u equals a to the v, then u equals v, which makes sense. If you have the same base and you have two powers, if the base to that power is equal to each other, then those two powers are equal to each other. So if I have 3 to the x plus 1, that's what that should say, equals 81. All right. So let's go ahead and look at how we might solve something like this. I see that my base is 3. When I have 81 is equal to 9 times 9, 9 is equal to 3 times 3 times 3 times 3. So 81 is also equal to 3 to the 4th. So if 3 to the x plus 1 equals 3 to the 4th, see where I'm going with this? Then we can set them equal to each other. So x plus 1 equals 4. Subtract 1 from both sides, and we have x is equal to 3. So that's how we're going to solve it. I'm going to give you a moment to look at this one. Okay, this is a little bit more complicated. Pause the video and see if you can go ahead and do that one. If you get frustrated, just pop back in and we'll go through it together. All right, let's take a look at B. What I notice here is that my bases are not the same, so I have to fix that. What I do know is that 2 goes into both of those bases, so 2 squared is going to be 4, and 2 to the 3rd is equal to 8. So I'm going to replace those numbers with 2 squared times 2x to the minus 1 and 2 to the 3rd times x plus 3. Now in our our log rules, or exponent laws, remember when you take a power to a power, you're going to multiply them. So this is the equivalent of 2 times 2x minus 1, and this is going to be equal to 3 times x plus 3. Now I have the same base, and I can set each of those exponents equal to each other. So 2 times 2x minus 1 is equal to 3 times x plus 3. And so let me go ahead and distribute these. I have 4x minus 2 is equal to 3x plus 9. I'm going to get my 3x subtracted from there, so I end up with x, and then add 2 to that side. So 9 plus 2 gives me 11. So x is equal to 11. So I'm able to solve those, what looks like horrendous problems. I'm able to solve them fairly easy by getting the same base and then setting those exponents equal to one another. Okay, well, now let's look at one that's kind of a little bit crazy. All right, again, this looks worse than it is. So this is pretty straightforward on this side. This side is a hot mess. So I'm going to go ahead and use some of my trig rules to kind of simplify that and see if I can, right? So I'm just going to copy this down, negative ex squared. X to the second power is going to be x times 2. And instead of putting x2, I'm just going to put 2x. So e to the 2x times that 1 over e to the 3 is the equivalent of e to the negative 3. Now what happens when I have two of those multiplied together? If it's the same base, I'm just going to add up my exponents. So I have e to the 2x minus 3. So now I have e to the negative x squared equals e to the 2x minus 3. Same base. So now I have negative x squared equals 2x minus 3. And now I'm going to move, it looks like this might be a perfect, or this can be factored here. X squared plus 2x minus 3. Yep, it can be. So x and x, and we have negative numbers. So one has to be positive and one has to be negative. The 2 is a positive, so this will be plus 3, and this is minus 1. So this is what it factors out to. And so if this is equal to 0, what would x minus 3, how would that give me 0? If x is equal to negative 3, and then x minus 1 equals 0, that is going to give me x equals 1. So my solution is x equals negative 3 and x equals 1. There's two solutions to this one. Okay? I know that was a lot, but you're going to be in good shape here. Okay, the last piece that we got to talk about is exponential probability. Exponential probability. So in an exponent, and this is also how your compound interest, all that kind of stuff is, right? So between 9 and 10 p.m., cars arrive at Burger King's drive-thru at the rate of 12 cars per hour. And it gives us the rate of 0.2 cars per minute. The following formula from probability theory can be used to determine the probability that a car will arrive within t minutes of 9 p.m. So remember, it's 0.2 cars per minute. I would not expect you at this stage of the game to come up with this, right? When I'm looking at probabilities, a whole or 100% would be 1. So I'm subtracting from that my probability of it happening, right? The following formula, probability theory, used to determine the probability that a car will arrive within t. Okay, so let's look at what happens if we're looking at 5 minutes. Will a car arrive in the next 5 minutes? We're just going to put in e to the negative 0.2, and we're going to substitute in 5 for t. Notice that when your input here is t, that's where that number is going to go. And if you go ahead and put this in your calculator, you get 0.63212. And that is a percentage in decimal form. So it's really 63.2% chance that in the next 5 minutes that you'll have a car, right? You can do it for 10 minutes, right? And it says they arrive at a rate of 12 cars per hour. So in 60 minutes, right, we know we have 12 cars. So we should be able to find the probability that a car will arrive in there. So again, go ahead and, right, take a look at that and approximate that value. Oops, sorry, not 5. We're substituting in 10. Okay, so what you are going to work on is my math lab for school.com, and you're looking for assignment 5.3 is going to be what you're looking for, okay? If you run into any issues or major problems, just go ahead and let me know in the group chat.